Hello and welcome everybody to my presentation entitled The Big Four Heavy Metals in Cannabis, Sample Preparation and Analysis via ICP-MS. You might have come across cannabis in a grocery store, in a dispensary or anywhere else. So as of today, I would say cannabis is literally everywhere. You can see it in food, used in sweets such as gummies or chocolate, in several kinds of beverages, but also in drugs, cosmetics, and personal care products. All of these uses make it, of course, necessary to test cannabis for their content, especially for content that might be harmful to people. And what's inside cannabis? That's a question you might ask. First of all, it's the cannabinoids. All of us know these. They're relevant because they responsible for the psychoactivity of cannabis, especially if the THC content is 0.3% or above, whereas you would talk about hemp in case of a low THC content. And we have got the terpenes inside, which are responsible for a so-called entourage effect. At least that's something that is under discussion. We have pesticides, which might stem from the process of growing residual solvents from an extraction process. For example, if you go for a high CBD oil formulation, then you would use solvents to extract cannabis. Heavy metals might also stem from the production or the growing process. And we also have mycotoxins, which might be generated by mold in case of improper storage of hemp or cannabis. Cannabis, we need to talk a little bit about anatomy, and that why do I want to talk about this? The reason is quite simple. Cannabis tends to accumulate heavy metals in its plant parts, and the accumulation of heavy metals depends on the plant part, and it differs from heavy metal to heavy metal. This is a small drawing of cannabis, quite old image, and what you can see here are different plant parts. That's the leaves. That's, for example, also the bud, including the flowers. And we got the seeds, and what is missing is the root. And all of these plant parts accumulate heavy metals, and that for that reason, it's also being used for the remediation of soil. That's an intended process, but it can also happen unintendedly, and therefore you need to test your cannabis for heavy metals. When I talk about heavy metals, I mainly talk about the big four heavy metals. The big four are arsenic, cadmium, mercury, and lead. And what we set up here is an ICP-MS analysis of these big four heavy metals. On the right-hand side, you can see four images showing a typical hemp bud. In that case, it's cannabis that is purchased from a grocery store. In Germany, this cannabis is sold as tea, so you can make tea out of it. And the first set of experiments is focusing on the analysis of such an entire bud. This is the variety Santica. There are different others, and we in total we're analyzing three varieties. Varieties can also be called as strains, or some also call them subspecies. In the second set of experiments, we segregated this bud into the leaves, seeds, and also into the stems. The reason for that is quite obvious. When you look at the products that you produce from cannabis, some only you make use of the seeds, for example, hemp oil. So it doesn't make sense to analyze the entire plant, but you need to focus on the seeds only. That's why we did the analysis of these three compounds. This is the ICP-MS workflow that we applied for the analysis of cannabis. It's a four-step process, starting with the sample homogenization. Normally that's a grinding process, manual or using a machine. Second step is the standardization and calibration. In that process, different chemicals come into play. For example, indium that we use as an internal standard. In that case, it's recommended to use a single element ICP-MS standard that is traceable. We use CertiPure or TraceCert. Reference materials that are available from MilliporeSigma under the trade name of Superco. We also prepare calibration curves, and in order to compensate for matrix effects, we use a standard addition approach. And for this approach, we apply certified reference materials which contain the big 4 elements in specific concentrations which correlate to the state limits of different US states. After this preparation of the sample and the standards, we start the sample digestion. In that situation, we use super pure or ultra pure nitric acid and hydrogen peroxide. Those are combined with the sample in the previous step, and then digestion takes place at approximately 300 degrees C using a microwave and under elevated pressure. And after that, subsequent ICP-MS analysis takes place. What I'd like to do is to focus a little bit on sample homogenization. I said we do a grinding process, and there are different options to perform this process. One very simple option that you might not have come across so far is to use a rolling pin. In that case, the sample is put into a Ziploc bag, stored in a freezer at -20 degrees C, and then you can crush the sample quite easily. Another option that many of you will know is the so-called mortar and pestle approach, where you apply a mortar and pestle to chop the sample, and more elaborated systems are knife mills or cryo ball mills, shown on the right hand of the image. There are, of course, some differences between these methods. First of all, the feed quantity. So the feed quantity is quite high when you go with the rolling pin approach, and it goes down to very small sample amounts of maybe a gram. When you apply a cryomill, in contrast, rolling pin can work with samples in the range of 5 to 10 grams. The temperature is -20 degrees C for the mortar and pestle and rolling pin approach, whereas when you apply a knife or a cryo ball mill or a ball mill, then you can cool during the milling process, in that case with liquid nitrogen at -20 degrees C, which is an advantage because high temperatures can cause decomposition of cannabinoids. Normally it's a decarboxylation, which of course then leads to a change in the sample composition. In addition, some of the terpenes are volatile, and so you can change the composition of your sample if you increase the sample temperature during the milling process. The efficiency of these different methods is strongly different. It's not very good for rolling pin and mortar and pestle approach, and becomes better when going to the right-hand side of this table. Best would be the cryo ball mill, and down below here you can see sample images that result after a milling process of about 5 minutes. Rolling pin and the mortar and pestle, it's quite inhomogeneous when you look at the images. The knife mill is better, and the best performance with particles of 100 micron or below will be obtained when applying the ball mill. So my recommendation in that case would be to go with a knife mill, at least if you have such a system in the lab. Do a pre-grinding process with this mill, and then transfer the sample to the cryo ball mill for final grinding. What you can see here are the results for different metals. In that case, all the 4 metals are listed. Calibration data is quite nice, very linear. Regression coefficient is close to 1. In that case, this is the data for the cannabis variety Vinola. It looks identical for the other varieties, so it's not displayed here. Now, let me come to the results of milling techniques. It's a comparison of these techniques. From left to right, you can see the rolling pin approach, then the mortar and pestle. This is the cutting mill, and this is the ball mill, cryo ball mill. Hemp variety is Santica. And what you can see is that the results are quite nicely comparable, with almost no cadmium abundant in the samples. No arsenic and mercury was detected. The only heavy metal that is at least available to some content or was analyzed to some content is lead. for all the 4 milling techniques, and you can nicely see that they provide quite similar results. For your information, the limit of detection for all the metals is 0.1 micrograms per gram, and we were in that case working quite close to the LOD. On the right hand side, you can see the Felina variety of cannabis. It's a quite similar result. We only found arsenic in one sample using the rolling pin, and for the others only lead was detected. When you look at the result for the mortar and pestle approach, the lead content is quite high, so it's 1 microgram per gram. That doubles the value for the Santica variety, and the reason for that most likely lies in an improper sample homogenization. As I said before, the plant parts accumulate heavy metals to a different content, and if you, in one case, for example, analyze an inhomogeneous sample which contains plant parts that accumulate a lot of lead, then this would cause these false results. So in that case, you would need to do better homogenization, as was done here, or you need to reanalyze your sample. This is not listed anywhere, but I made a comment here. The recovery rates are quite nice for all the elements, plus minus 10%. A second set of experiments, as I explained before, is the comparison of different plant parts doing the very same experiment. The only difference is that these plant parts were not ground. So no milling took place. That was not necessary because we handpicked the different pieces, stems, seeds, and the leaves, and we did 2 experiments each. And the only metal that was detected in any of the samples was, in that case, lead. Recovery range was better, even better as compared to the previous samples, 96 to 103%. And what is quite astonishing, and what is also in line with literature results, is the low lead content of the seeds. So that is known to the literature, and we found the very same situation here. What is a bit sad is the fact that we work with food. So as I mentioned before, all the samples that we used here are meant to be used to prepare tea. So we didn't expect them to contain large amounts of heavy metals. So for a better comparison, it might be nice to have real samples that were used for soil remediation. Might be an option for our next set of experiments. Last but not least, a little summary for you. I showed you that we established an ICP-MS workflow for the analysis of the big 4 heavy metals in cannabis. In that case, cannabis sativa plant material. The homogenization was reproducible in most of the cases, except for this one experiment using the mortar and pestle approach. The digestion protocol was specifically adapted to the needs of cannabis, as it is a quite smeary material. We adapted the digestion protocol using highly pure acids and hydrogen peroxide. And last but not least, something that we used in that approach was the standard deviation approach to analyze the heavy metal content, simply because we wanted to attribute for any matrix effects that we might observe. But not least, and this is the final slide I would like to present. If you need any further information about the Sigma Ulrich MilliporeSigma cannabis activities, then I'd ask you to visit this landing page. It combines not only the work that we've done on heavy metal analysis, but also all the other compounds that play a role in cannabis analysis. So the cannabinoids, terpenes, also the mycotoxins, pesticides, and so on. With that, I'd like to finish my presentation, and I'm happy to take any questions. Thank you.
Hi, everybody. My name is Kathy Stenerson, and I am an analytical science liaison with MilliporeSigma. And today what I'm going to demonstrate for you is how to use a technique called solid phase microextraction to sample terpenes from hemp flower. So first, what is solid phase microextraction? Well, for short, we call it SPME. And what it is the heart of it is a coated fiber device, like you see here, that contains either a polymeric coating or a particle type coating. And this coating extracts analytes from samples either through immersion directly into the sample or holding it in the headspace over the sample. And then after extraction is complete, the device is taken over and injected into a GC inlet just like a syringe, and the thermal energy of the inlet then desorbs the analytes off, and you can do your chromatography. So it's a really easy technique to do. It doesn't require any solvent, and the best part is these fibers are reusable. So it is very inexpensive. It's not like SPE where once you use the cartridge you throw it away. Okay, so the heart of the device are the fibers, the SPME fibers, and I've got 3 different types here, and by types I mean that they're coated with different materials. It can be a polymeric coating or a particle coating. Now when you buy SPME fibers, to know which kind you have, of course it'll be written on the box, but once you take them out of the box, they should have different colored hubs. Like here I've got red, black for carboxin, red for PDMS, and then blue for divinylbenzene. And that denotes what kind of coating you have. Now for today, I'm not going to get into a big discussion of what kind of coating to choose for what, because we don't have enough time for that. But for what we're going to do for sampling terpenes out of the headspace over hemp, I'm going to use something called a carboxin fiber. Okay, this is a very retentive fiber, and it's very good for very volatile analytes. So I'm going to install it in my SPME holder, which I have disassembled here. So the first step is to thread it onto the plunger. So the plunger's got a female threaded fitting, and I've got a male threaded fitting on the end of the fiber. So I depress the plunger to bring that female fitting out, thread my fiber on the end, pull the plunger back up. I'm going to put this nut on the bottom next. Just hand tight is fine. And then this plastic depth gauge. Okay, I've now got the assembly all installed in the holder, and then to expose the fiber I just push down on that plunger, and you can see the carbon fiber, which is black, exposed out of the needle. So our next step then is going to be to get our fiber ready to use, so we're going to condition it to clean it off. Okay, so I've been conditioning my carboxin fiber I installed in the holder for about 45 minutes now. And that, like I said earlier, that is to clean the fiber off and get it ready so that we can sample with it. So at this point, I've got it in a hot GC inlet. That's what I'm using to condition the fiber. And my inlet I've set to 300 degrees centigrade. I have flow going through it. That's very important. You want to have flow going over the fiber while you're conditioning it. And I've exposed the fiber by pushing down in the plunger. Now I'm going to take it out of the inlet, and one thing to always remember when you're doing manual SPME, retract the fiber back into the needle before you take it out of the inlet. Otherwise you're going to destroy the fiber. So I've just done that by pulling up on the plunger, and now I can safely pull it out of the inlet. So at this point then I'm going to go over and set up my sample, and I'm going to get it ready for headspace sampling. Alright, so I've conditioned the SPME fiber that we're going to use, and now I'm going to actually do an extraction. Now what I did before you were all here with me was I took about 115 milligrams of this hemp that I have here, this ground hemp, and I put it into this vial. This is a 4 ml vial with a septa cap, so that's a cap with a hole in it, with a nice thick septum that's Teflon lined. So that way, when the terpenes start to come off of the hemp, they'll be contained in here and they won't leak out, and we'll be able to sample them. And then the next step after weighing my hemp into the vial was I put it on this heated block, and I have this block at 40 degrees centigrade, and I let it sit for 10 minutes. I'm giving the terpenes time to volatilize out of the leaves, flower material, and to enter into this empty space, which we call the head space over the sample. So now I'm going to actually expose the fiber to that head space, and the terpenes are going to be extracted by the coating on the fiber, by the carboxin coating. So to do a manual extraction is pretty easy. I've got this nice setup which is commercially available that holds the SPME holder quite nicely. So the first step is you want to twist the top part of your holder and make what we call the needle part very, very small. The idea is that you don't want to be putting a long needle down through that septum because your chances of bending it would be fairly good. So now I've made it very short. So I'm going to open my holder and put it in. And then at this point, it's directly over the hole in the top of the vial. So I'm going to twist on the silver part on the top, and what's that going to do is it's going to cause that needle to come down, and it's going to go right through the septum. It's going to puncture the septum, and you'll hear a popping sound when that happens. You might not hear that with all the lab noise, but if you were up close to it, you would. So at this point, the needle's coming down, and it just went through the top of the septum. So I give it a couple more twists, and now I'm going to press the top of the plunger and expose the fiber. It's down inside the vial. I twisted it into the notch to hold it in place, and now I'm going to let that extraction go for about 10 minutes, and then we're going to desorb it into our GC-MS. All right, so the extraction time is up, and we're ready to go ahead and take the fiber out of the sample and desorb it in the GC-MS. So we're going to retract the fiber back inside the protective needle. So right now the plunger's down, so I'm going to bring it back up and open up my holder so I can pull it out and just take it right out the top. And then we just walk over, and we're going to repeat the process but into a GC inlet. All right, so I'm over at the GC-MS system now that I'm going to use for the analysis. So I got the fiber that we just exposed to the sample, and I'm going to set, there's a gauge here, we call it a depth gauge, and what I'm going to do is twist this big black plastic piece until I have my needle at the proper depth for the type of GC I'm using. Now this is an Agilent GC, and we recommend setting the depth gauge at 3. The reason being is that when I expose the fiber down in the inlet, it's going to be in the hottest part of the inlet, so you'll get the most efficient desorption. So next step is to inject it just like a needle into my inlet, and then I'm going to push the plunger down and expose that fiber. So I'm injecting it here into my inlet, push down on the plunger. Now it's inside the inlet, and I hit start. So now my analysis is going to proceed just like it would with a regular syringe injection. Okay, so right now the analysis is running, and I just wanted to show you real time what's going on, and the first sets of peaks are starting to come off from our hemp sample that we did SPME on, and there's a rather big one now that threw everything off scale. So what I'm going to do now on the software is I'm going to go down and take a snapshot what's going on here, and I can see a chromatogram real time. So this great big peak right here just came off. So I'm going to take a spectrum of it. This is a single quad GC-MS. I'm running it in full scan mode so I can get full spectrum here. Got a nice spectrum, so I'm going to library search that. And it's telling me it's beta-myrcene. So that's my first big terpene that I'm seeing come off of this sample. So we'll let you join up again when we get some more peaks. All right, so now we've got another cluster of terpenes that are eluting, and a rather large one, as you can see here. So I'm going to do the same thing again that I did before. I'm going to take a picture real time. So there's our first 2 big terpenes that we saw. The first one we saw was myrcene. The second guy, if we do a search on that, or take spectrum, do a search, that one it's saying is limonene. So that you would expect to find something like that. Now this big terpene here, this one, actually, if you take spectrum, it looks like it's probably pure. It doesn't, not co-eluting peaks, but let's take a search of that. And that's caryophyllene, which is pretty commonly found. So we're getting really nice terpene profile, as you can see. And the sample preparation was minimal. We didn't even use any solvent, which is really nice. So just another aside, too, is over here the instrument. This GC-MS system that I'm using, a single quadrupole, it does have an auto sampler on it. Now SPME, you saw me doing everything manually, but you can easily automate SPME with an XY type, Z type auto sampler like you see up here. But today I wanted to show you how to do it manually. So when you first get into the technique, you can just buy a holder and some fibers. It's pretty inexpensive, and try it out, work out your method. And then if you want to go the next step, then you can invest in the auto sampler. So next thing is I'm going to show you when the run is done. I'm going to show you the hemp compared to a lavender flower that I did the same technique on earlier today. All right, so earlier today, I did this SPME technique on some freshly cut lavender flowers that I cut from one of my flower pots at home. And I just put a few of the purple buds in one of those glass vials and just did that extraction the same way that you saw me do it for the hemp. And I wanted to show you what the terpene profile looked like compared to the hemp sample that we just did. So over here on the bottom chromatogram, that is lavender. The top is hemp. So you can see that they're very distinctly very different. Mainly this great big peak here, this terpene that's present in the lavender is not present in the hemp. And when I searched this was a linalool acetate, which you would expect to find in lavender because that's a very a prominent terpene in that particular type of fragrance. So this SPME technique can be used for basically telling things apart and fingerprinting different varieties of hemp or cannabis, being marijuana. So you could use it for that. As far as being quantitative, today what we did was qualitative, but the technique is definitely quantitative. It just involves a little bit more work because you have to prepare standards and extract them with your SPME fiber. But we have plenty of information on that, so please contact any one of our team members if you're interested in SPME or learning more about it, like quantitation or fiber choice or anything like that. So with that, I thank you for your attention and wish you all a very good day.
Welcome to Cannalab. My name is Rafael. In this talk, I will be sharing some tips and tricks for setting GC-MS instrument parameters for terpenes and cannabis analysis. I hope that you find this information informative and that with these tips and tricks, you continue to advance your laboratory productivity by reducing unnecessary downtime. The life science business of Merck KGaA, Darmstadt, Germany, operates as MilliporeSigma in the US and Canada. Let's take a look at the agenda for this presentation. We'll take a look at the introduction, talk about terpenes and its testing. We'll take a look at the sample preparation that's used for this analysis. We'll discuss the GC-MS instrument conditions, and then we'll take a look at the analytical results. Let's discuss the workflow for terpenes analysis. First, we perform sample preparation, followed by GC-MS instrument analysis, which allows us to detect and calibrate our analytes of interest and achieve consistent results. Terpenes are a large and diverse class of organic compounds produced by a variety of plants and some insects. They often have a strong odor or aroma to them. Although sometimes used interchangeably with terpenes, terpenoids or isoprenoids are modified terpenes as they contain additional functional groups, usually oxygen containing. Terpenes are hydrocarbons. Terpenes are also a major biosynthetic building block. For example, steroids are a derivative of the triterpene squalene. Here are the analytes, terpenes and terpenoids, analyzed from cannabis flower, which we'll be discussing throughout this presentation. Let's talk a little bit about the nomenclature of these analytes. Terpenes contain C10, no substitutions, for example, canphine and limonene. The sesquiterpenes are the C15 containing analytes that have no substitutions, for example, alpha-cedrine and beta-caryophyllene. Diterpenes, those with C20, such as phytol, is a diterpenoid since it contains an OH or hydroxy group. OH, hydroxy, or keto group substitutions make these species terpenoids. Let's take a look at the sample preparation steps. How do you get terpenes analytes in a vial for analysis? There are many different possible ways to get analytes extracted prior to analysis in terms of sample preparation techniques available to us analytical chemists. There's SPME, or solid phase extraction, which my colleague spoke about. There's solid liquid extraction. There's CEGERS, stands for quick, easy, cheap, effective, rugged, and safe. There's pros and cons to this technique when applied to cannabis flower. And there's SPE, or solid phase extraction. There's also diluting shoot. However, that's not a viable option for this particular matrix. A more important question becomes, how do we get what we want inside the vial while at the same time minimizing the components and matrix that we do not want? Our selected method of sample preparation was based on how do we maximize analyte recovery, what would maximize instrument uptime, what is feasible, and what customers were already doing in the marketplace or were willing to try. For our extraction procedure, 1 gram of cannabis flower, which was finely ground, was weighed and placed in a centrifuge tube. To this, we added 10 mils of GC grade ethyl acetate to each tube and cap. We sonicated for 15 minutes, then we centrifuged the tube for 5 minutes, and we transfer 1 mil of the supernatant to a 2 mil autosampler vial, and we cap. Our working standard solutions were prepared from Cannabis Terpene Standard Mix A and B certified reference materials available from MilliporeSigma Sapelco, and these were at 2,000 micrograms per mil. We made dilutions in ethyl acetate GC grade, and we ensured that these were placed in amber vials. From the working standard solution, we generated calibration standards in the following range, ranging from 0.75 to 100 micrograms per mil, or 0.75 ppm to 100 ppm. Let's take a look at the GC-MS analysis. The GC-MS instrument conditions. Please note that we utilized a 20 meter 0.18 SLB5MS column. The inlet temperature of the GC was 300 degrees C, and the flow was kept constant at 0.75 mils per minute of helium. A 2 microliter pulse split 50-to-1 injection was used. It is very important to note that the 300 degrees C temperature is necessary on the inlet to ensure that some of the analytes, in our case phytol 1 and 2, are readily transferred onto the gas chromatograph column and reaches our detector. Let's take a look at the extracted iron chromatogram of the terpene standard mix. We can see our first analyte, alpha pinene. We can see our internal standard, in this case tridecane, elutes at about 11 minutes and elutes right in the middle of the chromatogram with no particular interference of the analytes. Our last eluting analytes, phytol 1 and 2, required a high temperature of 300 degrees to ensure that they eluted from the column and into the detector. Let's review the detection and calibration. In this case, we see alpha pinene. We see the levels from 0.75 ppm to 100 ppm, and we see that 3 replicate injections at 50 micrograms per mil is very highly reproducible. In this case, we use M sub Z 93 for the quant iron and M sub Z 105 and 125 for the qualifiers. Please note that you can perform this analysis in SIM or scan mode. However, SIM will give you higher sensitivity. However, SIM will not provide you with library hit matches. So if you want to go ahead and search NIST or Wiley or other libraries, you would have to perform full scan analysis. So I would recommend using both the SIM scan approach that most instrument vendors provide as an option. Here we can see that for alpha pinene, the RSDs were 3.52%, linearity R square 0.999 in the range of 0.75 to 100 ppm, the LOD at 0.25 ppm, and the LOQ at 0.75. Let's take a look at the internal standard response reproducibility. As we mentioned, tridecane is used as an internal standard throughout this analysis, And as you can see from the reproducibility of the retention times, as well as the reproducibility of the internal standard response, it is very highly reproducible for injections over a calibration range. This is one of the critical attributes that you should be on the lookout when you're developing a GC-MS method. Ensure that you have extreme relative retention time reproducibility as well as response reproducibility. In this case, we're taking a look at an overlay of 3 sample injections showing repeatability. Even with matrix interferences, the method reproducibility is easily achieved. Sample preparation and robust GC inlet conditions are key in order to achieve this. Note here that the larger sample components do not interfere with the quantitation and identification of the terpene analytes. As you can see, CBD cannabidiol is one of the major components here. However, it comes out, the retention time is not anywhere near our analytes of interest with the terpene components elute. Here we can take a look at the extracted compound chromatogram of the hemp sample. As you can see, we have tridecane with no interference right in the middle of the chromatogram, and we have our alpha pinene in the front and our phytol 1 and 2 in the back of the chromatogram. Phytol 1 and 2 would be very challenging to do via the headspace GC-MS technique. It's possible, but you're gonna run into some issues in terms of using the high temperature on your vials as well as your transfer line for the headspace analysis. If you perform full scan analysis during GC-MS, you have the ability to create a customized mass spec library, which allows for faster analysis time because you're using a shorter library as compared to using the completeness libraries to search. It allows for retention times to be saved as part of the library, and it facilitates analyte identification. In this case, we're taking a look at the spectra for alpha humulene. On top, we see the NIST library spectra, and in the bottom, we see the spectrum of our sample, and you can see the high library match factor of 98.9 for alpha humulene. And this allows us to achieve consistent results. Having a robust method of extraction, as well as a robust method of instrument parameters in our GC-MS systems allow to obtain results that are very linear, very reproducible, R-squares greater than 0.39 and above, in the range of 0.75 to 100 micrograms per mil, and the RSDs are typically lower than 5%. In order to achieve these results, it should be noted that sometimes, in order to be in the linear calibration range of your instruments and avoid instrument saturation as well as carryover, you should dilute your samples to low levels. I would top it off at about 250 ppm, or use a high split ratio of 50 to 1 or 100 to 1, depending on the target levels that you're trying to reach in your samples. As you can see, even for the late eluters, phytol 1 and 2, the R-square value is there, the range and the reproducibility is there as well, and our tridecane as an internal standard served as a good way to keep our calibration ranges very linear over that particular range. In conclusion, a fast, efficient, and highly reproducible quantitative GC-MS analytical method was developed for the analysis of 31 cannabis-related terpenes. As it can be seen from the illustrations and results above, utilizing GC-MS in combination with Sopelco chromatography consumables, solvents, supplies, analytical reagents, and certified reference standards provides an efficient way to analyze cannabis products for terpenes in order to meet the current cannabis product labeling requirements. Reaching low quantitation levels of 0.5 micrograms per gram or 750 ppb is easily achievable, and obtaining all consumables and reagents from one supplier ensures that time is spent analyzing and running samples rather than finding multiple sources for your required analytical supplies. Keep in mind that utilizing a 20 meter 0.18 GC column provides maximum chromatographic resolution of the terpene analytes and facilitates adding additional analytes in the future if necessary. Here's a product list of the consumables and supplies and reagents used for this analysis, and you can find more of this information in our cannabis landing page at sigmaaldrich.com/cannabis. Thank you so much, and I look forward to any questions you may have.